Hello everyone. Before commencement of the next lecture of thermodynamics, lecture number 8, let's come back to lecture number 7, where in its fifth slide there was a typing error. Okay, so let me make correction of that error before commencement of the next class. So this was the covering slide. Okay, cover slide, and this one was the first slide. Now second slide, move on to second slide, third slide, fourth slide and fifth slide. So those who have already watched video number 7, already taken note, may have noted this error here. In this line, differentiating both sides with respect to t and p, the reverse process was followed in the next step. But here it was written the same procedure: first temperature, second pressure. That means with respect to temperature and pressure. But actually what happened, you had to differentiate both sides with respect to pressure at constant temperature. Okay, so that was the mistake, So here in place of temperature you have to write pressure, and here in place of pressure you have to write temperature. Then everything would be okay. So the correction is follow. This is the correction. Okay, here now this is the corrected form. So please make correction in your previous note from the lecture of previous lecture, and then let us move on to the next lecture, that is the lecture number 8 of thermodynamics. Hello everyone. In the 8th lecture of thermodynamics, our today's topics are perpetual motion of first kind, first law of thermodynamics, and some corollary on the first law and some special cases. So first of all, before the first law, we have to have idea about a machine which can yield work without supply of energy. This machine is called perpetual motion of first kind. And in reality this machine is not possible. Suppose some external agency is not aiding a machine, and in spite of that the machine is working, then this type of machine is called a perpetual motion of the first kind. That means there should be some perpetual motion of second kind. So we shall discuss about that one before the second law, but right now perpetual motion of the first kind, which is in reality not possible. Now move on to the first law of thermodynamics. This law states that the heat taken up by a system is equal to the sum of the increase in internal energy of the system and the work done by the system. That means actually the equivalent law among heat and work. If you have 1 calorie of heat energy, then in return, if you spend 1 calorie of heat energy, then in return you will get 4.2 joule of work. Now sometimes this 4.2 joule sometimes deviates a little. Then that deviation is adjusted by the change in internal energy of the system. And as we know that neither any kind of energy nor any kind of matter can be destroyed nor created, so that thing is exactly reflected in this first law of thermodynamics. So suppose a system is absorbing some heat and in return it is performing some work, and if the work and heat are equal, then it's okay, or equivalent, then it's okay. But sometimes if more work is done, that means the internal energy has decreased, and if less work is done, then the internal energy somehow increased. That means this increase or decrease, extra work or less work, has been adjusted by the change in internal energy of the system. That is why the heat absorbed by the system is actually the change in internal energy and the overall work done by the system. If you here mention instead of absorbed heat released by the system, there also here the change in internal energy plus work done on the system, you can write. Both the statements are correct. So how can we express this mathematically? You can express this mathematically. This Q is the heat absorbed and delta U is the change in internal energy, whereas since the work done by the system according to the IUPAC convention should be written in negative sign, so it is minus W. So this is the mathematical form of the first law of thermodynamics. Okay, Now this mathematical formula can be modified a little if the changes are infinitesimally small. Then you can write also dq equals to du minus dw. Okay, and this w or dw, if purely mechanical work, that means if it involves only pressure and volume, then instead of minus dw you can write p dv. That means p is the pressure, external pressure against which the system is working, and dv is the change in volume. Then minus w is actually plus p dv. So instead of minus dw you can write plus p dv. Okay, and if the change is finite, that means instead of dv the overall volume change is v2 minus v1, instead of du the overall internal energy change is u2 minus u1, then u2 minus u1 is delta u, v2 minus v1 is delta v. So in that case the volume change, for finite volume change, you can write the overall heat absorbed is equal to delta u plus p delta v. So these are the finite changes. Now the corollary. What about the corollary of the first law? That means the conclusions you are drawing from the first law. So if the internal energy changes by the internal energy change by the system is delta u, and the same by the universe, that means if the system is having some change in internal energy, then the surrounding, that means the rest of the universe, is also having some change in internal energy, and this is if denoted as delta u prime, then delta u is q plus w, because q had been delta u minus w, so delta u equal to q plus w, and simultaneously the heat is being absorbed by the system, that means heat is being released by the surrounding. Work is being done by the system, that means minus w, here it becomes plus w. In that case work is done on the surrounding, that means here plus w was accompanying delta u prime, so here minus w is written along with minus q. So in that case you can easily see that if you add them up, then the left hand sides would be delta u plus delta u prime. On the other hand, the right hand sides would become 0. So the corollary is the neat energy of the universe remains constant. Okay, suppose the energy is coming from the sun to the earth. Okay, that does not mean the energy of the our solar system is increasing. The overall energy is always constant. Okay, just some energy is released by the sun, and that much energy has been absorbed by the earth. So if you take into account the overall energy of the universe, this overall energy is always constant. Now move on to some special cases. These special cases are adiabatic case, isothermal case, cyclic process, and mechanical equilibrium. Then in those, that means isochoric, and not isochoric, that means actually delta p is 0, that means isobaric. So these 4 cases we shall discuss here. First of all, let's take into account the adiabatic process where q is 0. Okay, if q is 0, then put this 0 value into the mathematical form of the first law of thermodynamics. So it will give minus delta u equals to minus w. Minus delta u is the decrease in internal energy, and minus w is what? The work done by the system. So if there is no heat absorbed by the system, then apart from that the system is performing some work, then that work would be done in lieu of the energy which is given by the internal energy. That means some internal energy is expended here. Okay, and in return, in lieu of that internal energy, the work is done by the system. So work done by the system is equal to the decrease in internal energy of the system if it is an adiabatic process. This is case 1. Now case 2 is cyclic process. In case of cyclic process, you know that u is a state function, so the overall change in internal energy u is 0 from the starting to the end of the process. So if cyclic integration of du equals to 0, then cyclic integration of dq must be equal to cyclic integration of minus dw. Just put the this cycling integration sign in the mathematical form of the first law. Okay, the mathematical form was dq equals to du minus dw. So just take the cyclic integration sign in the left hand side of all the parameters here, and since cyclic integration of du equals to 0, so you get as a result cyclic integration of dq equals to minus cyclic integration of dw. That means what? That means the overall heat supplied to the system is equal to the overall work done by the system. That means there is no internal energy change. Finally, you are given 1 calorie of energy, in return you are getting 4.2 joule of work. Okay, so this is the case 2 where it's a cyclic process. Now move on to isothermal change. In case of isothermal change, the temperature remains constant. That means T2 minus T1 is equal to 0. That means delta T equals to 0. And from the Joule's experiment, this Joule's experiment would be discussed in the next classes or next lectures. So just take the result of the Joule's experiment or conclusion from the Joule's experiment, that if the temperature is constant, in that case the internal energy change is 0. Okay, so in that case Q equal to delta U minus W. Since delta U equals to 0, so Q equals to minus W. Or vice versa, minus Q is also equals to plus W. That means if heat is absorbed, then work is done by the system, or if heat is released, then work is done on the system, but there should be no change in internal energy. That means here again the equivalent relationship between calorie and joule. Okay, that means heat absorbed by the system is exactly equal to the work done by the system, or vice versa. Vice versa means heat released by the system is exactly equal to the work done on the system. Okay, and finally the case 4. In case 4 we are having isochoric change. The isochoric change means there is no volume change. V2 minus V1 equal to 0 or dV equals to 0. Okay, so if dV equals to 0, then PdV is also equal to 0. And if PdV equal to 0, then Q equals to delta U plus PdV. That means delta U plus 0. That means Q equals to 0. That means you are consumed to the overall heat energy, and in return you are doing no work. So the whole energy would be deposited to the body of the system as its internal energy. So heat absorbed by the system is equal to the increase in internal energy of the system. Okay, so that's all for the first law of thermodynamics. Thank you. Have a nice day.